Now it's time to start our last session for the day. So I will ask Wuji to start sharing with the last two presentations, then the poster, then the discussion. So we first start with Wuji Wang, who's going to talk about a massive galaxy at redshift 4.5 and its CGM. Take it from here. Thank you.
Okay, thank you very much. My name is Wuji Wang. I'm a PhD student at Heidelberg University. My supervisor is Dominika Velisalik. We also closely collaborate with Joel Vernet and Carlos Debrick at ESO. First, I would like to thank for the organizers for giving me the opportunity to talk about my PhD work at this wonderful conference. My PhD work is generally about galaxy evolution and aging feedback. To be specific, we look for high redshift radio galaxies. High redshift radio galaxies are basically the type 2 quasars with very powerful radio jet. Some of the jet can be as extended as several hundred kiloparsec. And the host galaxy of these very powerful radio quasars are very massive in stellar mass. Some of them can be as massive as 10 to the 12 solar mass. And they already established such a high stellar mass in the very early universe, like redshift 3. All of this evidence makes the high redshift radio galaxies a very unique laboratory for us to simultaneously see the quasar mode feedback, radio mode feedback, and the host galaxy. Yeah. In my work, we have a sample of 8 high redshift radio galaxies with MUSE observations. And here the movie is showing the MUSE theta cube of all of our sample targets, and it's looking around their rest frame Lyman Alpha emission wavelengths. And as you can see, this Lyman Alpha emission halo of the radio galaxies are very extended in size. Some of them can be extended as 100 kiloparsec. And when the movie looking around, you will see the Lyman Alpha halo is getting dimmed sometimes. This is due to the neutral hydrogen absorptions or H1 absorbers. And we often find also the mental lines or mental emissions in these emission halos, and that's probably give us a hint that the halo have an inner origin from the center of the AGNs. So it could be due to outflows. And next, I'm going to say something about our recently published paper last year. In this work, we mainly focused on one of our 8 sample targets, namely the 4C04.11 at redshift 4.5, our highest redshift target. On the right-hand side, you see the again the narrowband Lyman Alpha image and overlaid with the radio jet contour, giving you an impression of how large the size is compared with the radio jet and the Lyman Alpha emission halo. And on the left-hand side, we have the 1D spectrum extracted from the center of the host galaxy, and are marked in red of the UV emission lines we're gonna focus on next. The first line is the brightest Lyman Alpha emission line. Here is a zoom-in version of the Lyman Alpha line. As you can see, the Lyman Alpha line is suffered from the absorptions. To describe the line profile, we need to take care of the absorptions. And by fitting the line, we can extract or by get the information of the underneath intrinsic emission from the Lyman Alpha by correct for the absorptions. The absorbers, we also can get the column density of them from the line fitting. But with MUSE is a IFU instrument, we can always do more because MUSE, we can get spatial information from that, from the data cube. And the next step is we spatially map the Lyman Alpha emission halo. And to do that, first we do the tessellation just to increase the signal noise ratio. And right now you can see we have a 64 tessellation bins. So from each of the 64 tessellation bins, we extract the Lyman Alpha emission line and face them like the trick we used before. And next is a result we get from the spatial spatial mapping. Right now I show you the map is for the intrinsic emission, so not the observed one, but correct for the absorptions. And on the left-hand side, just a Lyman Alpha surface brightness map. And on the right-hand side is a WAT map, which is a non-parametric line width measurement. And I just point here that the WAT or the line width is higher in the southern part. So it's, as we know from the radio, the southern part is radio jet is approaching us. So maybe give us a hint, the jet gas interaction in this part of the halo. And next is our most interesting result we find is that we map the column density of the observer one. Just a reminder, the observer one on the left-hand side, again, is the observer near the velocity 0. And on the left-hand side is the column density map of our observers. So we identify a column density and from the southwest to the northeast. And for this observer, we also find the a tentative velocity gradient along the radio jet. So that's maybe give us a hint that the jet gas is interaction there. And here I just show you some example for our individual fittings from the outskirt of our Alpha emission halo in the low signal noise part. So you can see how the individual fit looks like. And here I'm not going to details about the metal lines due to the time that I have, but I just want to point out here that from the carbon 4 and nitrogen 5, we also find the absorber of the metal in these lines. And from that, we basically constrain the metallicity of the observer one, which is around the solar metallicity. So from all these observations, evidence we find, we come up with a toy model to explain all the observations we see. So basically it's what we call the outflow shell model. So in this model, as a sketch showing here, the observer one is basically ejected or outflow Gaussian shell, as probably by a previous AGN episode or star formation activities. And the column density we see, the column density gradient we see is due to a geometric effect. As you can see in the north, where the column density is high, our line of sight intersect with the gas much, it keeps decreasing to the south due to the geometric effect. And in the south, where the radio jet later on maybe get into the gas and leading to jet gas interaction. So makes column density is low, even lower there. And the metallicity, as I said, is probably give us a hint that this Gaussian shell is have an inner origin from the host galaxy. So from this observation from this paper, we are finding the evidence of the enrichment and redistribution of metals in the interstellar medium or even to the circumgalactic medium part. And this is only about one sample galaxy in our MUSE sample. We also have another 7, so we can, next step is to do the similar trick for all of our sample targets. And the next is we're very excited to just show the news here because we proposed and successfully get the GALAXIES cycle 1 observation time. In this observation proposals, we focus on 4 of our sample targets in our MUSE sample. So use near-infrared spectroscopy on board of GWST to really zoom into the center of the host galaxy to see how the feedback is established from the center of the galaxy to the outskirt and compared with our MUSE to see how the feedback is propagated. So hopefully we can get the data soon later this year. And I think I'm running out of time, so I just leave my summary here and thank you very much again for listening to my talk.
Thank you very much. Are there questions? So while we wait for some questions to pop up on the Q&A, I may ask you a question. So you have this radio data for the jet, and how well can you constrain the 3D morphology of the source and the inclination of the jets, for instance?
Oh yeah. Let me go back, or maybe just leave here. So yeah, the 3D morphology of the jet, or how the jet, the physical length of the jet is to my knowledge, is something we don't currently know for the time, as we know it's just a projected jet set as I show here. So yeah, it could be tricky to see what the inclination angle is, but from our knowledge, we know it's basically a type 2 quasar, so we're not directly looking to the ionization cone. So we probably have some constraint of the projection, but its details is not very clear.
Thank you. And we have time for one more question from Valentina Dodorico. She says that it's a very interesting result. And if you see the C4 emission also in the 2D MUSE field.
Yes, we can also map the carbon 4 in 2D. There's some information I don't show in the 8-minute talk, but basically in the absorption part, we can also find slightly some gradients there, but the result is not robust. So the signal noise is not high. We can just get some upper limit constraints here. Just so we do see the 2D.
We lost you for.
Okay. Yeah, can you hear me?
Okay. Yes. Now yes.
Oh yes. So just as I said, yes, we can see the 2D. So it's described in the paper, and probably my connection is not stable.
No worries. Thank you very much. And any other questions, please feel free to add them to Slack. And we can move on now to the last full talk for today, is from Manuel Solimano. Please.
Yes, thank you, Kara. And hello, everyone, and thank you for giving me the opportunity of presenting my work here, which is about a very peculiar high redshift object, and in my opinion, very interesting object that we have been calling the Kraken internally in our group, because someone in our group saw the figure of an octopus in one of the early plots that we made. And this monster in question is just a pair of star-forming galaxies that are embedded in a Lyman Alpha halo, and this Lyman Alpha halo is stretched and magnified because of the effect of strong gravitational lensing. And in this talk, I will explain how we combine this effect with high-quality MUSE observations to probe the gas properties down to kiloparsec scales. And why do we care about Lyman Alpha halos? Well, they are pretty common on the sky. A result from a few years ago says that mostly all of the sky is covered by these Lyman Alpha halos. Now with instruments like MUSE, we can observe them individually. And they come, of course, in a great variety of sizes. They trace the CGM. So large halos have very large Lyman Alpha halos, like the ones that we saw today by Fabrizio and now by Wuji. But we also have Lyman Alpha halos on a smaller scale, galaxies, isolated galaxies. And simulations show that they may have a lot of structured filaments and satellites. But these are often missed in observations because of resolution effects. So one way to get over this is to target strongly lensed Lyman Alpha halos. And this was first known by Swinback back in 2007. And since the upcoming online of MUSE, this has become a very efficient way to probe the spatial properties of these halos. And the major results are that these halos do many times have spatial variations, significant spatial variations across the halo, and they also have offsets of the Lyman Alpha peak with respect to the UV continuum. And the official name of this thing is QGACT2022. It was discovered a few 10 years ago with the Lyman break technique, and follow-up spectroscopy showed that these are in fact two galaxies. This southern arc is a second galaxy. The first one is multiply lensed. HST also shows a very clumpy UV continuum. and SED fitting with magnification correction, just that this system in total doesn't have more than 10 to the 10 solar masses and a stellar formation rate that is consistent with the main sequence. Both galaxies look very similar in terms of color and mass, but this galaxy B has a shallower UV slope and also a dust detection, so we expect it to be a bit more dusty. In the source plane, the two galaxies are separated by less than 15 kiloparsec, and also the difference in systemic redshift is very small, so all of this suggesting that they are interacting. But we have 5 hours MUSE observations, 5 hours in depth, and when we collapsed the data cube at the wavelength of Lyman Alpha, we found this. We saw this, a very extended and nice extended emission around the arcs with several features. For example, this one here, that we saw it was a candidate for a satellite galaxy that they were predicted by simulations. Emission, Lyman Alpha emission coming from satellites of these halos. And in fact, we went to look for a continuum counterpart, and we found it by removing the light from the galaxies of the cluster, and we found an excess in the blue filter of the ACS image. And this has all the properties that we expect for satellite galaxies of these inside this Lyman Alpha halo. And we now constrain that this contributes about 2% of the total Lyman Alpha luminosity. Then to investigate the spatial variations of the Lyman Alpha shape, we did a tessellation in the source plane, and we extracted the Lyman Alpha profile in each of these beams. And we saw this profile that is very redshifted and asymmetric, and also we characterize this Lyman Alpha line with these models, parametric models of asymmetric Gaussians. So we could build these maps of, for instance, surface brightness, line width, and also the shift with respect to systemic redshift. And we saw that near the continuum, the width is smaller, the line is narrower than at the outskirts. And something very similar for the peak shift, because these two things are correlated. We see that there's very nice correlation between width and redshift of the line, and that is consistent with previous work. And also the surface brightness is higher where the line is narrower. Finally, for a more physically motivated modeling and to break the degeneracy between, thank you, between the column width and the column density and the velocity, we employ these relative transfer models that assume a galactic wind geometry, and we see that most of the variation would probably come from velocity gradients that point out to an outflow. So scenarios for explaining the kinematics, we have ruled out inflow and inflows because we don't see a blue peak in the Lyman Alpha line, and we also don't see redshifted absorption in the UV metal lines. Instead, for the outflow scenario, we do see the red dominant peak, and we do see these blue shifted lines in the UV spectrum, and that have velocities very similar to the ones suggested by the models. And also we expect to see some signature of the merging, but we don't really know, because that will we will need to know the internal kinematics of the galaxies to see if there is any disruption or if there is unordered motions of the gas between the two. So we don't know. I'll leave you with my summary. We studied a pair of maybe interacting pair of SFGs inside the Lyman Alpha halo. We find a redder and broader line toward the outskirts of the halo, a global outflow signature, and models that allow up to 350 kilometers per second, with the confirmation in continuum of a small satellite that contributes 2% of the total luminosity. So, but more than answers, we got questions with this thing. We want to know if the merging activity is doing something, if the interaction is doing something, and for this we obtain time for ALMA C+ observations that will hopefully tell us something about the internal kinematics of the galaxies. And also we would love to know what's the contribution of fluorescence, or what is the escape fraction of the Lyman Alpha photons, and what are really the sources of reionization, because we have assumed that these are powered by star formation, but we don't really have very strong constraints on the AGN of a maybe hidden AGN being here. And these two questions will probably get answered with the upcoming GWST data from this early science program that will get IFU, near-spec IFU data on one of these two galaxies, and a lot of broadband data. So thank you. I'm happy to take any questions.
Thank you very much, Manuel. Very nice work, very interesting source. Are there any questions? I don't see hands risen, or while we wait for the Q&A, I may have some questions. So you're going to target the C+ line. So do you have like any idea potentially of like more denser molecular gas emission?
Yes, we actually in the past we observed this source with ACA, with the compact array at ALMA targeting CO lines, and we didn't find any detection. Only the dust detection that we think comes from the southern galaxy, but what we didn't detect CO 524 that we think I think we targeted. And also I know that in the archive there are some other observations for other lines like C1, and they were not detected. But for the C+ line, there's a Herschel observation that detected the line. So that's why we are pretty confident that there is some C+ coming from this source.
Interesting. Cross my fingers that that's the case, and you have. But anyway, you
Yeah,
will have wonderful new results to show with all of this data coming in. Okay, thank you again. And again, any other questions will be on Slack. And maybe we can move then to the poster session. Okay, thank you very much, Sophia, for sharing this and organizing this. So I will go through the list that I have here, and for each poster, there's a 1-minute presentation. So let's start with Vale Gonzalez.
Thank you. Hello, everyone. My name is Vale Gonzalez Lobo. I am a PhD student at the Max Planck Institute for Astrophysics in Garching. Here I show you my work on large-scale gas reservoirs around high redshift sub-millimeter bright galaxies with PLT MUSE. This work focuses on the direct study of the circumgalactic medium of massive high redshift galaxies in Lyman Alpha emission. In particular, we observed with MUSE a sample of galaxies with different degrees of quasar contribution, one an obscure quasar with an SMG companion, 2 sub-millimeter bright quasars, and 1 SMG without quasar contribution. Here are the Lyman Alpha Cypher's brightness maps of these targets, which all are expected to all live in similar dark matter halos at this redshift. And so we discussed the possible powering mechanisms of the extended Lyman Alpha emission. We characterize this Lyman Alpha emission and suggest that the extent and brightness of this nebula are likely regulated by their quasar contribution, followed by resonance scattering of the Lyman Alpha photons. So I invite you to check out my poster, and thank you for the attention.
Thank you. Spot on 1 minute. The next one is Jeyan Kartaltepe. I hope it's right.
Hi, everyone. With this poster, I would like to introduce Cosmos Web, which is an approved 218-hour JWST Cycle 1 Treasury survey that is being led by Caitlin Casey and myself. Cosmos Web will be the largest area observed by JWST in its first year and will cover a contiguous 0.6 square degrees with NIRCam and 4 filters and 0.2 square degrees with MURI within the Cosmos field. So this large area will form the base of the extragalactic wedding cake and will be complementary to a number of other smaller area, deeper surveys, such as Sears and Jades. Caitlin will tell you more about our science goals shortly, but as a large treasury program, our data will be fully public immediately, and our team is committed to releasing timely data products that will enable countless science projects for the community. So we welcome any input. Please come check out our posters and feel free to reach out to either of us if you have any questions. Thank you.
Thank you very much. Now we move to Jenny Swedi.
Hello everyone. My name is Jenny Swedi. I'm a graduate student at University of Uppsala, working under the supervision of Robert Tassi. The main intention of this project is to investigate the density of W2246 0526 environment by studying the surface density of Lyman galaxy. So we have the deep image W2246 0526 in RIZ band from Gemini Timor South. So we used the OG2000 for Lyman galaxy selection criteria. Due to the difference of the filters, we modified the OG criteria, then as shown in the color diagram. So we found 50 Lyman galaxy candidates. Afterward, we try to count the number of the Lyman galaxy within 20 arc second radius to determine the density of our target as a function of distance with W224605. So according to our results, the hottest obscure galaxy lives in the environment. So we compare the density of the universe. So however, the initial findings suggest that the overdensity of not clearly concentrated around the hottest. So if you are interested and have any questions, please look at the poster and contact me.
Thank you, Jenny. Now to Kathleen Casey.
Hi, yeah, thanks. So I'm Caitlin Casey at UT Austin. Just piggybacking off of Jehan's introduction of Cosmos Web, I'll tell you a little bit about the project goals of this 0.6 square degree JWST survey. Our first and primary goal that's probably most relevant to this conference is that we expect to detect thousands of EOR galaxies in Cosmos Web, particularly between redshift 6 and 11 is where we think we'll do best. And Cosmos Web will be particularly useful for mapping the large scale distribution of galaxies spatially, understanding their overdensities, underdensities, and correlation with reionization bubbles. We also have exciting projects related to identifying the rarest quiescent galaxies and massive galaxies at redshifts 4 to 6, and using weak lensing to reconstruct the stellar mass to halo mass relation around redshift 2.5. But you know, the legacy of such a program will really be wide reaching. So we're excited for the community to use it.
Thank you, Kathleen. Now the next one is Ashwara Girdhar.
Yeah, hi everyone, I'm Ashwarya Girdhar. I'm working at the European Southern Observatory, and I would like to present my work as part of the Quasar Feedback Survey, which is basically studying 42 powerful quasars that are highly bolometric but are radio quiet. Next, please. So I'm basically studying one of the galaxies that has radio, ionized, and molecular gas. And next, please, what I'm actually studying is I have the ionized gas kinematics that are compared with the stellar kinematics, and then I also compared it to the molecular gas kinematics. Next, please. So the main thing that I want to highlight for you is that we see this turbulent gas, which is perpendicular to the radio jet, which is very much inclined into the disk of the galaxy, less than 5 degrees. And as you can see in the higher panel, it's a way more extended in the ionized gas than it is in the molecular gas, which is in the lower panel. So with that, I would like to finish, and I invite you to please take a look at my poster, and also the paper is on archive. I put the reference at the bottom, and I'm happy to take questions. Thank you so much.
Great, thank you. 1 minute. Okay, let's go to the next with Michele Perna.
Hello, I'm Michele from the Center of Astrobiology in Spain. My poster presents some results from this PUMA project. PUMA aims to investigate multi-phase ISM physical and kinematic properties in nearby Urix using MUSE to trace the ionized and neutral gas, and ALMA to trace the molecular gas. PUMA consists of 25 Urix selected in order to include an equal number of systems with AGN and with starbus in the nuclei, and in the pre and in the post coalescence phase of major mergers. The results shown in the poster regard the incidence of ionized and neutral outflows, of kiloparsec scale outflows, also some first hints of the outflow driving mechanism, and the incidence of the perseverance of the regrown stellar and gas disks. If you are interested in this project, please have a look at the poster and also to the references here in the bottom. Thanks.
Thank you, Michele. The next one is Francesco Salvestrini.
Hello to everybody. I am Francesco Salvestrini, postdoc at the INAF Observatory in Florence. In this work, I study a sample of local obscured AGN, and I study also the effect of the presence of the AGN on the host galaxies' ISM properties. To do so, I applied a multi-wavelength approach, where on the one hand, I determine the AGN intrinsic power by using new and archival X-ray observation. Next, please. Thus allows me to also to determine the fraction of local Compton-Tick AGN. On the other hand, I use new and archival CO spectroscopy to determine the molecular gas content, as well by using the Spitzer area IRS spectral decomposition to determine the PAH emission. Then I compare the properties, such properties for my sample of AGN with a control sample of star-forming galaxies in order to highlight the effect of the presence of the AGN. So thank you for the attention. You can find my contact in the poster.
Thank you very much. Next one is Camilo Vasquez.
Hello, my name is Camilo Vasquez, and my poster is on multi-frequency imaging of kiloparsec scale jets in obscured radio powerful quasars. My research is based on a sample of 156 WISE and NVSS selected quasars with host galaxies that we believe have recently triggered AGN, are undergoing post-merger obscuration, and contain compact radio jets. This is why we believe that they are unique targets to investigate jet-driven feedback in quasars. A follow-up high-resolution VLA survey was conducted on the sample, which revealed that 80% of the sample contained compact radio morphologies and 61% showed peaked or curved spectra, which is consistent with young AGN. A subsample of 20 sources was selected from this survey, which brings me to my research, which is on a double compact steep spectrum source with a dense interstellar medium as seen in ALMA. And the goals for my research are to probe the radio structures and spectral maps of the source and eventually compare them with the CO line maps seen in ALMA. And here are some images you can see on the left, and the spectrum I produce of the source are my poster as well.
Thank you very much, Camilo. Super on time. Now to Victoria Fawcett.
Hi, my name is Vicky Fawcett. I'm a final year PhD student at Durham University, where I've been studying red quasars and how these differ from the more typical blue quasars. So first of all, we find that red quasars have enhanced small-scale radio emission compared to blue quasars. And the top right, I've shown a comparison of two radio images. In the other part of my PhD, we also have been studying the spectroscopic properties. So the top left graph shows two VLT X-shoot composites where we show that red quasars are red due to dust reddening. And I also show a comparison to our latest DESI red quasar program. So this is a composite where we show that with DESI, we're pushing to much more obscured systems than what we can find with SDSS. So overall, we find evidence that red quasars may represent this special phase in the evolution of quasars. And I'm happy to discuss this more, and I encourage you to check out my poster. Thank you very much.
Thank you a lot. And now our last poster, Takuma Itsumi.
Hi everyone, I'm Takuma Itsumi from Managed Round. Our team has been studying low luminosity quasars of redshift 6 to 7 universe, which will provide a less biased picture of early growth of black holes and their host galaxies. In particular, I've been doing ALMA, C+ and fine for the continuum observations. In the top left figure indicates C2-based dynamical mass versus black hole mass of high-C quasars, color-coded by UV magnitude. And if you assume that dynamical mass is a surrogate of bulge-scale stellar mass, you see that luminous quasars tend to show overmassive black hole relative to the local co-evolution relation, the diagonal line, whereas low luminosity quasars tend to show consistent or even smaller black hole to host mass ratio to the local relation. And we also found a very broad C+ component in one quasar, which is suggestive of outflow. And we also found a very clear case of galaxy-galaxy interaction that harbors a low luminosity quasar, which may be a progenitor of extremely luminous quasar population. And this would be the key to think about early co-evolution. And let's discuss more in Slack. Thanks.
Thank you very much. Super on time, all of you. Thank you for keeping that. And thank you in general for all of the presenters, talk presenters, poster presenters of today's session, and everybody that interacted and assisted, because I think we have a lot of food for thoughts regarding environment in general, as we have seen in all these very, very interesting new results, but also summary of what was done before. So I would like to open the floor for a bit of a discussion here, because I think there are many things and many arguments that were raised today regarding especially quasar environments, and I'm biased here, I admit, that is worth discussing on. So I have prepared a few slides just to guide the eye, and I also have a few questions to submit to all of you, because I have myself a lot of more questions than what I have put, but let's try to make it interactive and see what each of us can bring. So all of the presenters are coming in, and I'll share my screen. Okay. You see my presentation or the slides?
Yes.
Okay. Thank you. Thank you very much. So discussion of the day 3. This is just like a presentation slide for the start of this interaction, because I think we have touched a lot of general discussions on a lot of general topics regarding the environment, and we had excellent talks regarding different subtopics of environments, let's say, from host galaxy and AGN, but also starburst interaction, the feedback and the outflows, and how these interact with the ISM of the host galaxy, and how this is resolved in the coevolution, as well as the CGM physics, and going on to larger scales, the quasar in galaxy environment, especially had the ice redshift, where now the questions are a lot, and also in general, how the environments shape galaxies that are in different environments, in voids versus over densities, and what are the first protoclusters, and also what does that mean regarding the IGN. And I've tried to put a bit like as sort of a summary, the different posters and talks we had for, or will have tomorrow for these topics, and I'm sorry if I missed any of you, I hope not. And I would like to first start, of course, like in all of this, please feel free to jump in and suggest any of your point of view. I'm very curious about anything that the crowd would like to discuss. I would like to first start with quasar and galaxies environments at highest redshift. And so I think that like the very first questions, the big questions that has come up also in the previous days is, do quasars at high redshift with high redshift greater than 4, 5, and 6, etc., reside in massive halos? This seems to be the naive expectation, quote unquote, as also Roderick was saying. And from larger sample and cross-correlation functions, as Christina was presenting us, it seems that this tool in particular is excellent in telling us that this is actually the case. There's a strong correlation between quasar and galaxies, and hence these quasar live in massive halos in this time. And at the same time, for instance, Wuji Wang yesterday presented us, I think, very inspiring new possibilities for JWST to do this sort of studies. And another point that has been raised in the history of the questions for quasars environments is if radiation has been suppressing galaxy formation. And we have seen in the different talks that now, and also the posters, that now this point seems to be less important, or less seen as possible, because many like galaxies have been found in the close vicinity of quasars, and also the other excellent points that were raised by Roderick in his talk. So considering all of this, I think I would like to start with a very general question, which probably we can keep on talking for days. So I would like to ask Jorge to pull out the Zoom poll right now. And this would be the first question. So, do the audience think that quasars live in massive halos at high redshift? So first, yes, but quasar radiation can hinder galaxy formation. Yes, but not in the center and not in the massive ones. Yes, but not, and still unclear, or no, this is bullets. Okay. Questions are starting coming in. I love the fact that we're all very confused in this and we're all very split. So anyone would like to jump in with some considerations?
A question, can you all see the results live? Or is just me as a host?
No, it's only panelists and hosts.
Okay.
Oh, okay.
Okay.
So you need to click end poll for everybody.
Okay,
sorry. Okay.
We have 57 replies already.
Yeah, I think somebody, the last 5 seconds, anybody would like to jump in? Okay, I think we can share.
Okay, ending poll.
Thank you. Okay, so we're pretty much split, I think, even if we're still unclear and inconclusive, gets the slight majority. Anybody would like to jump in?
Well, I'll be provocative and just say something.
Yeah,
I think it's very plausible that they do live in the very rich environments, but perhaps not the richest of all, but generally in rich environments. But to be provocative, I guess I might argue that this isn't so surprising. We know quasars like to live in massive galaxies. We know that massive galaxies like to live in rich environments, and there you are. Well, I guess I might question whether that's an informative thing to know or not. It's good it's practically useful if you want to churn out structures at high redshift by searching around quasars. That's a very good thing. Practically, it's a useful thing, but physically, does it mean a whole lot? Well, I mean, that would be an interesting question to kick around. But again, I'm being provocative deliberately, perhaps.
No, please be so. And on my point of view, one very interesting thing that Roderick had on his talk and also in his paper, I think it was a very nice paper, is that for the formation of the first supermassive black holes and this immense first black holes in the first quasars, it's sort of like necessary, quote unquote, for them to be in special environments. So like on the informative part is that how can we use this, like do we need them to have this these first black hole seeds, and how can we use this environment to search for not only the properties of the first galaxies, but also the potential answer to the question, what were the first seeds? I'm sorry, like while sharing, I cannot see if you have like hand raised, so feel free to really jump in. Radek.
Yeah, so one question I have here is to what extent these the seeding of these black holes in simulations is still a rather manual process, right? In awful lot of simulations, it's still assumed, right, that the most massive black holes start out in the most massive halo or the largest overdensity on some scale. And one question I have, mainly I guess directed towards the theorists, is how much freedom we have in this. So if you let go of this particular seeding mechanism of selecting the largest overdensity and then populating this with some black hole, whether you get into trouble. Because I think what mainly sets the black hole growth is the host halo, which will guarantee a very high accretion rate. But you can have that I imagine in a massive halo, also if it doesn't sit in a larger scale overdensity.
I think Melanie would like to take it from here.
Hey, hi. Yeah, I think it's a very good point. I think in simulations at the moment, there is really a gap between, small scale simulation where you can test different seeding mechanisms, but then you don't have the volume, the needed volume to actually form quasars, and then larger simulation that do start having a large volume, large enough to have really massive black holes, but then on the other hand, we're just putting by hand black holes in all galaxies. So I think at the moment in simulation, we still have this gap that we need to fill to really try to connect the seeding to high redshift quasars. Yeah.
Melanie, but what you just said is that the high resolution simulations don't have the volume sufficient for forming these black holes. Isn't that based on our expectation or desire to sort of mimic this co-moving density of 1 per cubic gigaparsec, something like that? So,
I mean, so to really study the seeding in simulation, you need a very high resolution, and that's why we cannot have a large volume. But if you don't have galaxy with stellar mass larger than 10 to the 10 solar mass, then I wouldn't expect a black hole to be 10 to the 8 solar mass or 10 to the 9, right? So I think we have this huge this huge gap. I don't think it's because of the number density. I think it's just a matter of what kind of galaxy you're forming in your volume.
Okay. Thank you.
Thank you, Melanie, for these insights into simulations. I mean, this is all super connected, even if, at least personally, I'm much more closer to the observational side and to the observational debates and questions that I'm more familiar with. So I think it's super important that we reach out to each other. So is there anybody that would like to add more, or should we move to the next topic, which is linked to this actually?
I would like to say something about this. I agree that most of the studies are still unclear and inconclusive when we look for galaxies around the quasars, but we don't have to, we need to remember that we also have a very well measured measurement of the clustering of quasars in the universe. And that is a very strong evidence that quasars trace massive dark matter halos. At least has been measured until redshift 4. Higher redshift is not very well constrained yet, but this is, I think, a very strong evidence and has been in agreement in different studies that quasar trace over densities. The reason why we are not detecting the galaxies around the quasar could be explained by several reasons, but we don't have to forget that piece of evidence that, in my opinion, is a very strong evidence.
Yeah, I mean, this is a super important point that you're sharing, Christina, and I'm looking forward to have more constraints of this at the highest redshift as well. Even if this is completely different than what we see at redshift 4, that would be very strange. At least would be interesting to explain. And this sort of connects to what is the next question and next argument that I have, next topic, which is, again, let me see if I can move on, which is galaxies around quasars at high redshift. So this seems to be sort of the same, but it's not exactly the same. So as Christina was saying, if we expect to find them, but we do not find them, how can we detect them? And we have seen in different, and what are the properties of these galaxies surrounding quasars? And we have seen several different points in this today and in general in the conference, which I think are really interesting. For instance, it seems that the luminosity and the masses can come in, that the brightest ones are favored to be found around quasars, and we have seen this in observations by Jackie and also simulations by Tommaso. And as well, it's important to consider the spatial scales that we're considering and the fact that many searches for photometric bays like LBGs, but also just galaxies detected in their dust continuums are not very conclusive in the presence of companion galaxies, such as instead spectroscopic and redshift line measurements are. I find that this is super interesting, that also the SMG search by Jackie, but also the ones found by Christina are not showing a lot in the continuum, and instead are showing in the lines, as well as what Roman was showing. So maybe is it worth it to go still for this type of searches, or is it just better to have IFU like ALMA or MUSE to search for these galaxies and search for the lines? And at the same time, the very important topic that we have seen everywhere is also the multi-wavelength aspect of this, and the search for different types of galaxies, LBGs, Lyman Alpha emitters, line emitters, etc. So, and sometimes we might also consider if that we are interested in finding the galaxies themselves, maybe we should try to look at the properties of the quasars also when we decide to look for their environments. For instance, are they radio loud? Are we expecting more sources around loud quasars, or around quasars which has larger luminosity, larger black hole masses? And so, like my second question is very, very practical, I think. And I would like to ask Jorge again to share it. So imagine that we have, as many of us as thought in the observational point of view, but I would be very happy that people from the theoretical side answer as well. We would like to devise like the ultimate response to this question observational wise. And what is the most urgent? Like, should we go for a multi-wavelength search? Should we go for covering both small and larger scales? Should we just go for IFU and maybe mosaicing of IFU like ALMA or MUSE, etc.? Or targeting specific samples, or targeting a lot of samples, maybe with shallower observations, or there's no galaxies, so who cares? So I'm very curious to come up with this, because I think this is a question that at least I am asking myself a lot, and that I'm sure the TAC would like to see answered in the proposals we write. Answers are coming in. Roderick, would you like to? Okay, maybe I'll just wait for like a few more seconds that more people are voting, and then we can move to the discussion.
I thought I was going to ask a question while people were thinking about their answers.
Oh, yes,
Okay.
please. Sorry, Roderick.
No, okay. I wanted to direct maybe a question towards Christina. So I think that the work at Redshift 4 that she showed, that's absolutely, I'd love to have this kind of statistics at Redshift 6, right? It's clearly where the field should be going. What I'd like to ask is, so we know of the Redshift 4 quasar population that the underlying halo mass distribution is quite wide. Translating to present day masses, I think it goes from, it has a median descendant of 10 to the 13 solar masses for a typical bright quasar, Redshift 4. So that's sort of a group-like environment. But it can be as low as 10 to the 12 and as high as 10 to the 14. But this is a very skewed distribution where maybe 1 or 2% of the luminous quasars of Redshift 4 are in sort of cluster-like environments today. So I was just wondering how this factors in, this sort of wide underlying distribution of halo masses factors into this cross-correlation type of work that you have been doing.
Yeah, I think that is a very valid point, because most of the work are targeting the most brightest quasar actually so far. And so definitely I think that as long as we're having more statistic and more targeted quasars, we can start to splitting the quasar sample to see if we detect some correlation between the environments and the properties of the quasar, such as the luminosity or, I don't know, other properties of the quasar itself. I think that we still don't have enough data to constrain that. But I agree that most of the work are focusing on the brightest quasars and on the unobscure quasars too. So we still have to target more quasar with a wider range of properties to really know how this impact in our knowledge about the environment.
Unfortunately, we don't have individual halo masses for quasars yet.
Yeah.
Thank you.
Thank you. We have 67% of the public voted, so maybe we can add and share. Thank you, Jorge, very much. So this is again very, very split. And this reassures me, quote unquote, because I'm not the only one that is conflicted about this. So it seems that the slight majority is for multi-wavelength observations, and just followed by a few in spectroscopic confirmations of this type of galaxies, and followed by multiscales. Not only 2 people thought to have a targeted subsample of quasars, but nobody thought there's no galaxy. So anybody would like to add in something? Feel free to.
Well, I'll say something. I mean, I voted
Yes.
for multi-wavelength, which I'm always a sucker for the multi-wavelength, I guess. But again, my personal feeling is, sure, it's great to churn out over densities of galaxies around these things, but I think you really want to know what does that mean? And until you can characterize these environments and measure stellar masses and so on, and star formation rates for all of these galaxies, it's very hard to even interpret what it means, because of all I mean, there are many correlates with black hole growth, And until you can unwrap those, it's going to be very hard to know at high redshift if you see overdensities of galaxies, what does that actually mean? Does that mean there is something special about the environment that makes these things grow better? Or is it just telling you that the galaxies in rich environments are the ones that tend to host quasars?
Yeah.
And so a multi-wavelength approach is the only way to get an answer to that, I would think. I mean, I'd like someone to push back against that point of view. I'm surprised that people aren't trying to tear my eyes out, because but
well, I would love to see somebody jumping on Zoom and tearing your eyes out. No, I'm joking. No, but to be honest, I'm quite intrigued by the multi-wavelength aspect myself, because when we have tried this, I mean, most of the time you start from something, right? So you maybe start from C+ over densities, and you look at those massive galaxies that are there and as bright as the quasar host in the millimeter, in the submillimeter, and then you go and look for the rest frame UV or optical counterpart, and you don't see anything. So these guys are extremely special galaxies that are already telling you something or a lot on what is going on, but at the same time, like I would still be curious, and this multi-wavelength aspect comes again to say, okay, are these the only type of galaxies? If I would have looked into it just with the rest frame UV and optical, I would have just said, oh, this field is boring, quote unquote. So I think there's a lot of potential to this, but at the same time, also an IFU perspective is important, I think, for the actual final, like realizing where these galaxies are. But like doing both of them and all of them at the same time is kind of, it is kind of impossible on the human scale, maybe, or maybe it is. I'm happy if somebody is against me here. Or if somebody finds a very good way of selling mosaicing MUSE or ALMA observations around high redshift quasars that talks seem to not like very much. Don't know if somebody else has something to add, their own experiences.
I was also torn on my response there, because I do think we should do all of them. So I think the multi-wavelength perspective is important, but I would also like to see getting consistent spatial scales for those multi-wavelength studies. So I do think that getting like ALMA mosaics of like single quasars that we're interested in to get to the same field of view that we're getting with, you know, some of the REST UV and REST optical observations would be important, because I'm interested in seeing whether you know, like the 3D distribution of these galaxies, whether you get like preferential filaments of like only submillimeter galaxies in like a different area than you might see, you know, with LBGs or more normal star forming galaxies. So I think right now we are limited by the smaller field of view of the long wavelength observations. And like we heard about today, like your overdensity signal is very dependent on the radius that you're going out to. So I think if we can get those observations to like a similar spatial scale, then it's important.
Yeah, I mean, very, very important as well. And as well as, I guess, after listening to today's talk would be to maybe sit down amongst all of us and decide the definition of basic things like overdensities, which are the spatial scales, et cetera, which seems to still be not so set in stone, right? And also another point very important that Christina raised is the fact that we can observe as much as we want of the environment of the highest redshift quasar, but then we would need to have a solid background to compare these two, which is again still work in progress. Somebody else would like to add something, or should we maybe go through? I have got another couple of questions, but given the time, maybe we can go to one more. Okay, then let me go to this third one, which is more about galaxies themselves. And what can we learn? What have we seen in these days about galaxies in different environments? So we have seen different talks, for example, today by Jetli, a very nice talk exploring what is happening in galaxies in void, as well as Lucia's sample in the first day on multi-wavelength observations of different galaxies in a dense environment, and the very nice talk today by Roderick going over our knowledge and observations of protoclusters, or let's say overdensities of galaxies over different redshift. And we have also seen from the posters today that there's going to be next very exciting surveys with new facilities such as James Webb, covering a large area that will for sure help us answer tons of questions, and the posters are really excellently done about this. But another very interesting talk was that from who showed us the Lager survey, and also pointing out the roles of these protoclusters in the ionization. And as yesterday Laura Penterici was pointing out, it's also a point of being able to observe, for instance, Lyman Alpha at the highest redshift. And lastly, Neil gave a very nice talk on the black hole accretion and growth and its dependence on the environment or the growth of the galaxies themselves, the stellar mass. So I have like very more general questions regarding all of these arguments. That is again more general, and maybe Jorge can help me out pulling it out, the Zoom pool. How do you think the environment influences galaxies? Like, is there an announcement of activities like star formation, AGN, black hole growth? Unclear, we don't know, which means that it diminishes. There's no influence at all. Galaxies don't know where they live, or it all depends on redshift scales of densities, etc.
Can I ask for a clarification on this question?
Yes.
Now, when you say there's no influence, do you mean there's no influence after you take out all other effects? Because I mean, there surely is an influence there. That's unquestionable. But it could be purely just a secondary effect driven by other factors.
Yeah, it's more a point, I would say, like no influence at all. Like you think that there's no influence between environment and any other effect, secondary effects, like not at all.
Okay.
Yeah, it's more it's more like a random point in this.
So maybe one way of phrasing it is to ask if you think there's any astrophysics that doesn't exist. New astrophysics that comes in dense environments that doesn't exist else otherwise.
Yeah. Thank you. Yes.
And what do you say if you think the effect is redshift dependent? You know, we know, for example, star formation is suppressed at low redshift, but maybe elevated at high redshift in rich environments. So you can't even answer. What redshift do you want this to be answered at?
Yeah, that's kind of like the last point, right? That's
okay, fine. I'll put it in there. Okay.
Sorry. Like, I don't think that we were always thinking that was the case, right? Because at least even when I started, it seemed that in the dense environments where there aren't that galaxies, right? But this is not the case at any redshift. So yeah, that was sort of like one of the discussions that I wanted to raise with this question. Yeah, I think that 60% voted, so we can start sharing. And indeed, the larger majority voted for dependence on redshifts and other points. Somebody would like to jump in? Also, Neil, if you like.
I've already said enough. I mean, you can probably predict what I'm going to say at this point, so I'll be quiet unless someone wants to provoke me.
No.
Well, it would be nice to hear some examples of those that select that chose anything other than there's no influence, which was me. But it would be nice to hear examples of things that are correlated strongly with environment somehow.
Well, again, I'll take, so star formation. Star formation does seem to be correlated with environment. It even, when I didn't present this in the talk today, but in that same analysis, to make sure that our analyses were reliable, we also did star formation correlations with environments, and we recovered the ones that people have known for many years. And so, I believe there is a connection between star formation and environment, but it doesn't seem to translate into an effect upon AGN.
Yeah. Well, for sure, there's I particularly like where it's clarity. Part of the introduction from Jackie Champagne's long talk on YouTube about the evolutions of how we see galaxies in clusters, and yeah, for sure the turning point of where galaxies in clusters, for instance, are being turned out, and galaxies in clusters are the ones really forming galaxies is really interesting to study in my point of view. But also I thought it was very important and interesting what simulations are telling us about void and galaxies in the void and galaxies not in the void, which I honestly don't know how much, I'm very ignorant. So I let Melanie move on about this because I don't know the state of the art in this.
Yeah, thanks. Yeah, so cosmic void, I think the talk was interesting, right? So what we saw in one simulation, our last case simulation, is that the galaxies in cosmic void, and here I want to specify that the void were smaller than the void that we actually observe in the universe because of the volume of the simulation. Yeah. But what we were seeing is that the evolution of the galaxies was late compared to other regions, more denser region galaxies. So because you have this late evolution of the galaxies, they are still forming stars pretty efficiently. And then the age and activity is also higher than for the same stellar mass galaxies somewhere else in the simulated volume. So this was interesting to see. I guess one motivation for that was initially, or can we learn about the seeding, the black hole formation with galaxies that are actually close to us? And one way to do this is by looking at dwarf galaxies because they are less evolved. They didn't have that many galaxy mergers in their history, so they still retain some of the initial black hole properties. So the mass of the black hole is similar to the initial mass and things like that. So expanding on those dwarf galaxies, we wanted to find regions of the universe that are really isolated with no interaction with the surroundings, and void galaxies are perfect for that. So it was a way of triggering new observation in void to get to know something about the formation of black holes. Yeah, but I think, yeah, the environment can influence somehow, star formation and age and activity to some level.
Yeah. Okay, so we have reached 3:30. If two participants raise their hand, please. I can't see who's came up first. Sorry. Maybe I can try to stop sharing. Okay. So I can see you. Okay, Jetri.
Okay.
Sorry if I'm butchering your name.
Yeah, no, don't worry. I was following the question that someone said about of course, star formation have a relation with the environment, but perhaps it's not. Perhaps it doesn't have to do with the black hole. I think that one way to disentangle this is, for example, to observe, for example, the metallicities or the gradients of the galaxy, because for instance, in Eagle, the relation between the black hole mass and the stellar mass, we have that this relation is flattening, but depends of the in higher mass depends of the AGN feedback. So I think a way to disentangle this is one, look at the secondary properties of the galaxies, and well, one thing that James was suggesting is also to look at, for example, these samples of star formation rate to disentangle between the star formation activity and the AGN activity.
Thank you, Anjali. And I think it's also important to talk between us about how much these observations should be exact in terms of systematic errors, for example, because I have the feeling that in many other points, especially at the highest redshift, it becomes really difficult to compare because of the large uncertainties that we have as well. So like continuous talking between, again, observers and simulators and theoreticians as well on the aspect of the more finest work will be interesting. Is anybody would like to, Melanie, are you still would like to intervene? Or okay,
I can just say something in reply to that. So to I guess Yetley, I think that's a good point. You know, in fact, when we started the work that I described, we actually originally thought about trying to correlate with star formation rate as well, because there seems to be pretty good evidence that black hole growth, you know, does correlate pretty well with the star formation rate of the bulge component, not the galaxy overall, but of the bulge component specifically. And the thing that we found, however, was that stellar mass by itself, which is also known to correlate with black hole growth. See, this is a multidimensional problem. You have star formation rate correlations and stellar mass correlations, and you're looking to see if there's environmental correlations. Well, but what we found was that stellar mass did such a good job of sucking up all the dependence that it left no room for any real true environmental dependence. And so we never pushed it further to see, well, should we also try to partial correlate versus star formation rate to see if there's anything to take out there? Because by the time stellar mass has had its way with environment, there was nothing left to go after. And so it would be interesting to go, you know, to have a battle, you know, just leave stellar mass aside and have star formation rated environment fight it out to see which one of those influences black hole growth further.
I would have then a question about this, like very, very practical. How would you compute the star formation, like from where?
Right. Okay. So clearly, again, you have to work in the fields with the best multi-wavelength data available. You know, the other reason why we favored using stellar mass first is stellar mass can be more straightforwardly computed than star formation rate. But for star formation rate, well, you know, you would ideally for the massive systems that are often highly obscured at high redshift, you would want to go out into the infrared, out into the far infrared as far as you can. So you do use Herschel, for example, to try to get it at star formation rates. And then as you went to lower stellar masses, where hopefully the obscuration isn't always quite as bad, you would then have to go and use full up SED fitting. And that would be, you know, dust corrected UV and things like that, which clearly I smirk at myself, but you're left with little else to do, because until you have super deep infrared, that's all you're gonna be able to do. So that's what I would try to do. Yeah, but anyway, it would be a good thing. It'd be a good thing to use Cosmos or whatever field really has the best multi-wavelength data for this, and to have a real battle where you have star formation rate in there fighting against stellar mass, fighting against environment, and see what emerges as the victor. I mean, I have a pretty good guess what would happen, but I don't know for sure.
Yeah, I mean, what you're saying about multi-wavelengths is like super important, and I hope that Cosmos Web, for example, is helping us in this.
Yeah. Well, actually, if the Cosmos Web people are still on, I'd like to hear what they have to say about this. I mean, will Cosmos Web somehow enable better measurements of star formation rate in some direct way, or are they able to speak, or they're not able to speak right now?
I don't see them in the panel, so
okay.
somebody raise their hands up to this. James, let's see if I can ask him in. Yeah.
I'm not a Cosmos Web person, but I was just going to follow up on what Neil was saying about it all being driven by stellar mass, because we do know that we see more AGN preferentially in star-forming galaxies. And as you've been saying, we know that galaxy properties, the quenched fraction, depends very closely on environment. So it almost feels like, is there not almost some little cosmic conspiracy going on? Is that as you move to a more dense environment, that we don't see an effect in the AGN fraction, that somehow the mass dependence, like you say, sweeps it all up and compensates for the change? Or is it just that it's the mass is driving things in the first place?
Yeah. Well, yeah, this is the great challenge of interpreting data. I mean, does correlation imply causation, right? I mean, all you can do is take the data you have in front of you and see what correlates the best. But again, correlation doesn't necessarily prove causation. So you can try to then set limits on how much there could be, but it almost becomes one of these semi-philosophical things of what does data really mean, and what do correlations really mean? I mean, do you have any reactions there, James? James, I'd be interested to know what you think.
I mean, I agree absolutely that correlation doesn't imply causation. I guess it's working out what physically is going on, what is behind this stellar mass dependence. And I think, at a fundamental level, we can understand that stellar mass dependence simply from the fact that more massive galaxies on average have more massive black holes.
Yeah.
So you can allow for that, and then that brings in a huge sort of selection bias and is a big part of why we see more AGN in more massive galaxies.
Mm-hmm.
So once you allow for that, then we do start to see a difference in star-forming galaxies versus quiescent galaxies. That does exist. Now maybe that difference is just too subtle, that therefore it doesn't translate into effect on an environmental effect, however you choose to measure it, whether from a clustering signal or directly measuring over density. There are various different ways of probing that environment, but maybe you just aren't sensitive enough to see it.
Yeah. Well, we did. Yeah, I certainly agree with you that there is that problem where more massive galaxies have more massive black holes, so that's where you get the growth. And so what you can do is try to, you make a two-dimensional grid of environment versus stellar mass, and then you look for any dependencies at fixed stellar mass or something like that, right? And even then, there doesn't seem to be much there. But then you run into correlation, causation. What does it mean?
Okay, I think that with this end note, I think it's perfect to end the discussion for today. And I thank you, all the participants, once again. And any other discussion can also be followed up on Slack. And maybe give back the word to Roberto if he has to, if you want to say something for the end of the day.
No, just thank everybody. This was a wonderful discussion. Thank you very much. So I think this is the end of the day. Tomorrow we start at 9 a.m. Eastern time, and the broad topic tomorrow is theory. So it'll be an exciting day as well, and I think we've prepared a ton of questions that we'll want to ask theorists tomorrow. So thank you everybody again, and we'll see you tomorrow.